Good morning to all. Today mainly we will discuss about the distribution system load flow studies, and later on we will discuss about the application of meta heuristic algorithm in power distribution system. So moving forward, initially we start with very basics about the power flow studies, then we will gradually move to distribution system load flow, and how this distribution system load flow is designed based on backward and forward sweep method. We will discuss about that. Now coming to the power flow studies or load flow studies, basically power flow studies or load flow studies, we can say it's an steady state analysis, and whose target is to determine voltage, current, real and reactive power flow in a system. Or in other way we can say to analyze and complete system, whether what's supposed to be the voltage, whether this voltage is within its boundary or not, to check those things, to identify how much power is flowing across the line, what is the power flow across between two line, and what's supposed to be its thermal limit, to identify those things. If we are supposed to incorporate any new circuit on a certain loading, what will be the scenario? If voltage is fallen to a certain part, whether we are supposed to integrate capacitor over there or not, those things we are supposed to check it there. Rather than this, we may say to identify the optimal rating and tap range of a transformer. What's supposed to be the optimal rating over there, we are supposed to check it over there, and thereafter we can utilize in a system whether any DG or distributed generator or any new capacitor bank is supposed to induced. Then what will be the scenario, what's supposed to be the its optimal rating, or what's supposed to be the its optimal size, this is supposed to be we have to identify. So generally when we gone for load flow studies, we generally use Gauss-Seidel methods or Newton-Raphson methods. But the issue with when we talk about the distribution system, as we know in distribution system, R by X ratio is quite high. Therefore, we may face certain problem. In Newton-Raphson method, X by R ratio is high, therefore its over decoupling effect is there. Ultimately, the Jacobian is becoming diagonally dominating. Therefore, this convergence become faster in conventional Newton-Raphson methods. But when we gone for the distribution system, in distribution system X by R ratio is very poor. Therefore, Jacobian formulation is become not that much diagonally dominated. Therefore, its convergence become slower. Therefore, to identify some alternative method is necessary. In direct way we can say high R by X ratio resultants of slow convergence, rather than most of the distribution system is having a radial and sometimes weakly meshed in structure. Their impedance across the three load is keep on varying. Most of the time it is an unbalanced system. So we gone for the specific programming based on distribution system load flow, and this program mainly developed based on backward forward sweep concept. Here generally when we gone for any distribution system, radial distribution structure is there, initially we calculate what's supposed to be the branch current on each node based on Kirchhoff current law, and after calculating this current across all of the branch, we calculate what's supposed to be the node voltage at all of the node. So as we start from backward side, this method is known backward, and thereafter we calculate the voltage at each node. Therefore, it's known as forward method. In details, I will discuss. If we see in this diagram, a normal single line diagram, it consists of we can say it's a normal 5 bus system. Mainly bus 1 is an distribution substation bus, and other 4 bus, if we consider it as an load bus. At that time, what we supposed to calculate here, if I consider at very beginning moment, we have considered voltage across all of the node is as Bs voltage, Bs at an angle working. Okay, no issue. This cut. Basically. Okay. If I can we remove this one? This cut.
वो पर लैपटॉप में आ रहा है शायद, इसमें आ रहा है क्या? Escape it. सब लोग आ रहे हैं.
Okay, now let me discuss on board. As
First, check that whether that slide is working or not. Slideshow is working in your laptop. Next slide is coming. Now it is fine.
okay, I will try to explain from here only. If we move to backward sweep method, and if we consider we are having an this system, where if you see there we have a 5-node bus system, and if I consider that initial voltage at each node is as BS node.
Check your laptop side. Just losing from that detail and
Okay, what I'm discussing initially, if we consider that voltage is our voltage is as BS initial voltage as a constant voltage, and then if we suppose to calculate how much current flowing across this current flowing across this path, if I consider this current is as I5, then it's supposed to be P5 plus J of Q5 divided by B of S. So if I consider branch current at this node as B of 45, so your supposed to be total current over there, it is supposed to be yes. Initially, I considered this current is as I5. So your I5 current we can calculate based on this P plus JQ5 of B of S. Thereafter, if I considered what's supposed to be the branch current, your current at node number 4, it will be something like that. P4 plus J of Q4 plus B of 4, whereas initial voltage for B of 5, B of 4, these all voltage we have considered it as an 1. Similarly, we can calculate the current for I3, it's supposed to be P3 plus J of Q3 into B3. Similarly, we can calculate what's supposed to be the current for I2. It's supposed to be P2 plus J of Q2 into B2. And as we supposed to calculate the branch current at this branch in between B of 4, 5, here our branch current, it will be B of 4, 5, it's supposed to be I5, whereas branch current for the B of 3, 4, it's supposed to be whatever the current flowing across this path I4 plus B of 4, 5. So it's supposed to be B of 4, 5 plus I of 4, or in other way we can say its current supposed to be I5 plus I4. Similarly, if we go on for the calculation for an branch current supposed to be B2, 3, it will be the summation of B of 3, 4 plus whatever the current flowing across this node. So it's supposed to be B of 3, 4 plus I of 3, or in other way we can write it out I5 plus I4 plus I3. Thereafter, if we write whatever the current is coming at this branch, if we consider this branch as the branch of I1 of 2, so this branch current will be something like that. Whatever the current flowing for it, if I consider it, this current as I2, this I2 plus B of 2, 3. So in this way we can calculate the branch current for all node. Branch current for all node, and this is the backward calculation we have carried out till now. Now thereafter, if we have considered this normal single phase line, it is this discussion till now, it is about the backward calculation over there. Now if we move for the forward calculation for node voltage of each node, as this voltage is known to us, now we supposed to calculate what's supposed to be the voltage at V2. This voltage V2 voltage, it's supposed to be the B1, it's substation bus voltage, whatever it's over there, minus of I1 into Z1. As it's single phase line, we may consider this Z1 is whatever the resistance and reactance across this path it is given. If the moment V1 is known, we can calculate it out the voltage for node number 3. This voltage is supposed to be the V2 minus I1, not I1, it's supposed to be the whatever the branch current it is over there. Actually, it's supposed to be the B12 minus Z of 1. It's supposed to be the B23 into Z of impedance over there, Z of 23, it's supposed to be 13. Thereafter, we can calculate it out, whatever the voltage for B4 node voltage, it's supposed to be the B3 minus branch current 34 into impedance of Z of 34. And then similarly, we can calculate the voltage for the B5. This voltage is supposed to be the B4 minus whatever the branch current B45 into Z of 45. So in this way, we have calculated out whatever the voltage on each of this node. Now, if we move a little further, initially we calculate stepwise calculation. If we discuss first step, it was about the assumption of voltage. Step 1, it was B assumption. Second step, it was calculation of branch current. Then step 3, we have calculated out node voltage at each node. Now in step 4, we will check the mismatch between each node voltage. Initially here we have considered voltage Vs at an angle of 0 equal at 1 per unit. Now we got the node voltage of all nodes, so we will check for the second iteration what supposed to be the V2 voltage in first iteration minus V2 voltage in second iteration. Whatever the mismatch is over there, what is the del V2 is over there. Similarly, we will check it out node voltage for node number 3, node number 4 and so on. At the end of this, we will calculate at step 5 if what is the maximum value of del V2, del V3, del V4 and del V5. If this maximum value of this is less than tolerance value, then we will stop the iteration. If it is less than tolerance value or not, that thing we will identify max of del V if I write it over there. So initially again we have to define this tolerance value in earlier, and if we able to achieve this one, then tolerance value less than tolerance value, we will stop the iteration and we will calculate whatever the node voltage over there or not. Okay, if it is not satisfied, then what we supposed to do? If tolerance value is moved, then again we have to go on for the earlier step what we have said. If I go to previous slide, then again in iteration 2 we have to start from this step. Now earlier one it was for iteration 1, here this will become for iteration 2. Now if I write for the next step iteration 2, then at that time your load will remain same, but here your voltage will keep on changing. Here initially you have considered voltage at 0th iteration, whatever the voltage you people have assumed it over there. Right now your this voltage will be based on the first iteration voltage. So here its voltage supposed to be the V1. For similarly for current calculation, for fourth node calculation, here also it will be I1, and similarly we can calculate it out for iteration number 2. And after calculating the value for iteration number 2, we will go for the calculation of node voltage at iteration number 2. Now here your in iteration number 2 node voltage will be V2 node voltage will be whatever the V1 voltage we have obtained earlier and whatever the branch current and impedance is over there. Now throughout this programming, this impedance is not going to change, it will remain constant. Whatever thing keep on changing, it's only about this bus voltage and branch current. Similarly, we can calculate it out for the node voltage for all of this iteration. So this is roughly if we write the flowchart for this. If it is satisfying, then stop iteration. If it is not satisfied this criteria, if it is yes, stop iteration and display a result. Display your result over there. And if not, then repeat it from step 2, and this cycle keep on going for a few time until and unless we have achieved our reach to our value less than tolerance value or not. Okay. Now as we know, in distribution system, most of the distribution system is unbalanced system. While we gone for the analysis, unbalanced system, that time what will be the rule of the impedance? Now if we go for the three-phase structure, if we consider this is a three-phase line, here if I consider this is a phase, and initially for A, B, C, all three phase it's okay, everything is well and fine from node number 1 to 2. Similarly for node number 2 to 3 also it's okay, but in node number 3 to 4 we can see there is only two line is over there, whereas at impedance for node number 4 to 5 it's a single line. Similarly from 3 to 6 is also single line. So what will be the size of the matrix of this impedance when we gone for the analysis for impedance? If I write for Z12 impedance, it supposed to be the 3 cross 3 matrix. It's supposed to be the Z3 cross 3 matrix, Z12 of AA, Z12 of AB, Z12 of SC. Similarly for Z12 for BA, 12 for BB, and Z12 for BC. Similarly for this one, 12 it is for CA, Z12 for CB, Z12 for CC. It will be the size of this matrix. And now if we calculate for Z23, what will be the its size? Again, similarly it is again 3 cross 3 matrix. But if we gone for the calculation for the Z34, at that time its size will be the something different because we are having only two lines over there. So this matrix size will be 2 cross 2 matrix size, 2 cross 2 matrix size, or okay, we can calculate it out. But for Z45 it will be the only single matrix, whatever the value of Z45 or impedance value, single matrix is, it will be there. And similarly for Z36, if I consider this is as Z36, it is again single size of the matrix will obtained over there. Now like earlier, here also if we solve, what value we may see change over there. If I move to next slide, here like earlier, here also we considered that initial voltage at BS at an angle of 0 degree, as of it is three-phase system. Therefore, we have considered the phasor difference in between 120 degree angle, and initially we set the iteration count as 1. And then we gone for the calculation of load current calculation. Like earlier, from nth node we start our calculation, and when we start our calculation from nth node, we consider there also at the very beginning moment B as a value supposed to be the 1 per unit, like that. Here also we considered kth minus 1 or 0th value. So this thing is known to us. P and Q value is known to us. So based on this equation, we can calculate it out, whatever the current for any node for all three phase. Then if we move from backward sweep method, and we supposed to calculate the branch current. So if I consider any of this line, we are having any of this line, we are having a node of M and node of N for all three phase, whatever it is. So we can calculate it out based on this calculation. For a phase, if I consider this is a phase, and this supposed to be whatever the and whatever the load is connected at nth node, whatever the load is connected at this node, plus how much current is flowing from beyond this point, and to above, how much current is flowing at this point. Similarly, we can calculate it out, what supposed to be the current for B phase and what supposed to be the current for C phase. And this calculation for the three phase scenario also can carried out based on backward sweep method. Then further we move ahead, and we have calculate what will be the voltage for each node. So as this voltage we are supposed to calculate at BAN voltage, we supposed to calculate if we consider M is our starting node. So in general way we can write this equation whatever shown over there. BAN is supposed to be the earlier node voltage minus whatever the impedance across this into whatever the branch current of this. Now this impedance, if we observe, this value of this impedance may keep on changing for a three-phase scenario, this impedance value. Other thing is for the almost remain same, but only change over there we will see on this impedance. And based, if impedance we have calculate earlier, then definitely we can calculate it out, what will be the mismatch voltage for kth iteration and kth minus ith iteration. K minus ith iteration voltage we have assume it, and right now we have calculate voltage for kth iteration. So from there we calculate it out, whatever the maximum mismatch over there. We can utilize this formula for all number of node, how many nodes is over there, and then we will check whether this is less than tolerance value or not. If it is not less than tolerance value, then again we will go to earlier step. Earlier step means this we will start our iteration count equal to k plus 1, and for second iteration we will go and we will start to calculate our load current, and then again branch current, and followed by the node voltage calculation. So that is okay. If any query regarding this? Okay, in direct approach based, the same thing. When we gone for the direct approach based distribution system load flow, direct approach based distribution system load flow, if we go, so what step we can supposed to follow? We can, like earlier we said, our demand is known to us, so we defined the demand. If we gone for the coding for this problem, initially we have to define this one, then we have to initialize our tolerance also, whatever the tolerance is over there. Then we have to calculate the node current. Here if you may see, this is an 6 bus radial distribution system. So node current in any node, if I consider for this node or this bus, we can write it out as I5. Branch current B5 is equal to, we can write it as I6. For branch 4, this current is I5. For branch current for B3, it's supposed to be I4 plus I5, whatever the current is over there. And for branch current at this node situated in bus 2 and 3, if I write, so it is the summation of all node voltage beyond this node. So it is supposed to be the summation of B3 plus B4 plus B3 plus B4 plus B5, or in other way we can write it out I3 plus I4 plus I5 plus I6 over there. Similarly, if we calculate what supposed to be the branch current at this branch, so it's supposed to be the sum of all this node current. Or if we prepare a matrix, if we called this branch current as a matrix, where it is shown in this equation, if I say it's equation number 3, so at that time branch current B1, it's supposed to be equal to B2 plus B3 plus B4 plus B5 plus B6. So we formulate in terms of a matrix of it. And similarly for branch current at B2 node, there we may see for B2 node I2 is not over there, so the value for I2 is written as 0. Similarly for branch current at B3, if we write its current over there, it is again 0, because it is only connected. While we are calculating the branch current, this current is supplied only to I4 and I5 current. So this two value is written as 1 and others are 0. Similarly for the calculation for branch 4, it's supposed to be feeding only bus number 5 or node number 5 current, so it is as 1 when it is I5 equal to 0. This matrix is usually known as BIBC matrix, bus injection branch current matrix we have shown over there. Now if initially we have to calculate this BIBC matrix, then if we move to next matrix calculation, this is calculated by BB matrix, and this matrix calculation is carried out based on whatever the node voltage over there. B2 node voltage is known to us, Um, how it is known to us, because B1 is always remain same, it's supposed to be the 1 per unit. So B1 minus whatever the branch current was there, B1 into Z12. Now if we consider it is unbalanced system, the value of Z12 matrix may change based on that. If for single phase system it's okay, there is no issue. Similarly, and there also we calculate voltage at node number 3, P3, it's supposed to be B2 minus whatever the branch current over there into Z of 23, Z of 23. And if we split this one, we can write it out like this way, because B2 is again a function of B1, so we can write it out B1 in minus B12 into Z12 minus B2 into Z of 34. Thereafter we have calculated out whatever the voltage at B4, node voltage 4, this node voltage 4 supposed to be whatever the node voltage at B3 minus whatever the drop across this line, and the drop across this line if I say it's supposed to be the Z of 2 to 4, whatever the value of Z of 2 to 4 we can, 3 to 4 we can calculate it out. Similarly we calculate for bus 5, this bus 5 voltage supposed to be B4 minus whatever the drop is over there, and finally we have calculate the voltage for bus number 6, and this voltage for bus number 6 is supposed to be the whatever the voltage was at bus number 3 minus whatever the drop is over there. Now based on this, if we shift this voltage on all this rearrangement, if we carried out, this matrix will be look like this, which is shown in equation number 4. So basically if we see this is mismatch between node 1 and node 2, B1 minus B2. Thereafter whatever the voltage is over there, we can formulate a matrix in terms of Z and in terms of branch current. So when we calculate the voltage for mismatch between B1 and B2, they are in between, we see it is only Z12 is presence over there. But if we gone for the calculate what is the drop between B1 and B3, at that time you may see over there Z12 plus Z23, the impedance for these two nodes are plays a role. Similarly, if we calculate the voltage for B4 with respect to B1, that time we have the impedance for Z12 plus Z23 plus Z34. Similarly, if we suppose to calculate whatever the voltage drop in between B1 and B5 in terms of matrix, then we will get the impedance for these 4 impedance we supposed to consider, and the same is shown in 4th row of this equation number 4. And like this way we have calculated out whatever the mismatch for bus 1 and bus 6, and finally we formulate this formula, and in smaller way if we represent this formula in terms of whatever the del V, if we write it is, and we can say it is BCBB matrix into whatever the branch current over there. So this matrix is here known as BCBB, branch current bus voltage matrix. So in earlier page we have seen how we can represent this branch current with respect to I. If you remember equation number 3, this branch current is equal to, we can write it's a BI BC matrix into I. So if we put the same value on this equation number 5, so it will be something look like what is shown in equation number 6. So in other way we can write it out, del B is equal to, it's an multiplication of two matrix BCBB and BIBC matrix, then it's supposed to be multiplied with I. And if we club up these two matrix, so we can write it out directly, del B equal to distribution DLF matrix if we write it direct load flow into I. So from this analysis, if we observe every time what change will obtained while we update our branch current or voltage, the impedance is not going to change over there. Impedance is remain same. Only change you will obtain your bus voltage is kept on changing. And based on this bus voltage, if you calculate it out, what will be the maximum mismatch over there, and if this mismatch is less than tolerance value or not. If it is less than tolerance value, then it's fine, stop the iteration, display whatever the voltage and current across all of this path. Otherwise we have to repeat it again, and this iteration kept on going unless and until it's satisfying this line. Okay. Now what is the advantage of this? As we seen here, Jacobian formulation part is not over there, and we basically carried out based on two matrix. One is BCBB and another is BIBC matrix. It's quite easier to formulate any programming, and its convergence also quite faster. So therefore most of the time in distribution system we use these methods. This method initially at 2003 JH Tang is proposed this method initially. Thereafter a few modification is also done on it, like sometime we may use double forward methods or some other methods we can use while solving this distribution system load flow. This is an general flow chart. This may help us while framing and code for this matrix in second half. Here we supposed to start with already we discussed the same. Whatever the system data is over there, here the system data is supposed to be your load data, it is supposed to be there along with whatever the line data is supposed to be for any system, and from there you are supposed to calculate whatever the node current is over there. Now then if you go and calculate a BIBC matrix based on backward sweep methods, and then calculate BCBB matrix based on forward method, then calculate direct load flow matrix, and after calculating the direct load flow matrix we set this iteration count actually, and we will update this voltage and check whether this tolerance criteria is satisfying or not. If it is not satisfying, we are supposed to update our all of this voltage based on again this all calculation, and then finally we will calculate whatever the line flow and losses or node voltage is over there. Now this is a general system. If we consider for an IEEE any system, 34 bus system or 69 bus system, in general scenario, if we see this whatever the voltage, next if I move, This is a single line diagram for an 34 bus system, and here in general total demand is around 4.6 megawatt active power demand, and reactive power demand is supposed to be 2.8 MVAR. At that time, on generally we obtained losses is around 221.7 active power loss, if I say. And minimum voltage as of it is distribution line, we can see the minimum voltage will be the bus which is far ahead from its substation. So its voltage, minimum voltage is coming ahead at 27 number of bus, and its voltage is around 0.94.17. Now if we gone for the bigger system, at that time voltage drop will be further. That time we may need to add a certain capacitor bank over there, or certain thing over there. So where we supposed to connect, and the moment we will connect, what supposed to be the reactive power injection, and based on that again we have to carry it out the load flow analysis, and we have to check what is the voltage, minimum voltage over there, or whatever the losses is there over there across the system. Now this is ideal scenario for an 34 bus system. We are not considered any injection over there. Now the moment if I want to reduce the losses for a distribution system, generally losses for distribution system is lies around in between 10 to 17%. So it's quite high. The moment we inject reactive power over there, our losses has been reduced a slight. So where we supposed to place those capacitor bank and those things, we can randomly we can put anywhere, but that is definitely not the solution. We may not get the best result over there. So we may utilize some optimizer algorithm to identify that exact location, which will help us to reduce the losses, at the same time to improve the voltage also over there. Now if lump sum we are not going to use optimizer algorithm, and I just put on bus number 27 a capacitor bank over there, a certain load data will be there. The moment I put the capacitor bank over there on bus number 27, what will be there? Our P demand and Q demand will remain same, but Q demand will change. And the moment our Q demand will change, again we have to carry out all of the load flow studies, and we have to identify whatever the losses over there and whatever the voltage on each of this node. So that time again we will have to go back to our backward forward sweep methods. The moment I have inserted any capacitor bank on node number 27. Similarly, if I insert this bank on bus number or node number 26, again we have to carry out this load flow, and we have to identify whatever the loss is over there. Therefore, in next topic we will discuss about the any optimizer algorithm, how it help us to identify the optimal location and what supposed to be the optimal range of that capacitor bank is necessary in terms of loss, in terms of cost, or in terms of voltage deviation. We will see it out. So till now whatever we have seen, we have discussed only about a tool which is computationally it's supposed to be faster, and convergence is faster, so therefore we can achieve our objective. Our objective is to carry it out the node voltage and active and reactive power demand, how much power is required, supposed to calculate this one, and we are able to do it out with the help of direct load flow method, which is formulated based on backward and forward sweep methods. And that's all. This is a general few line about direct approach for distribution system we can utilize instead of Newton-Raphson's. Newton-Raphson also Okay, not many problem, but sometimes it's not converged. It got struck due to different survey X ratio. Here, for formulating or designing this tool, we can utilize two metrics. One is about the DIBC matrix, that is, we can say bus current injection and branch current relation between B and I, and another was it was about the BCBB matrix, and this BCBB matrix actually it was a relation between branch current and bus voltage, and by combining of these two we can formulate this direct approach for solving any load flow studies. Okay, that's all for distribution system load flow. Now in next part we'll discuss a little about the optimizer algorithm. If anyone is having any query, please. Hmm? Yes, we'll solve in second half on MATLAB. This one we'll solve at least. Yes, yes, absolutely. Yes. Now, when EV is over there, it may work as a source as a load. Now, where if I consider the same system where we have used 34 bus system, if we connect in any of the node this EV is there, in certain interval it's supposed to be charging. So therefore, it's work as a load. The moment it's work as a load, for that interval our scenario will be something different. Again, we have to carry out this load flow studies to identify whatever the losses and whatever the supposed to be active and reactive power demand over there, and voltage. It will act as a load. In next interval, if EV is not there and maybe it is selling its power to its grid, so we will consider it as a source. So at that time our equation will be something like that. Whatever the substation is feeding, P substation plus PEV is supposed to be equal to P demand plus P losses. So we have to satisfy that equation when EV is working as a source. Okay, coming to the optimizer, let's start or need some break? Yes, sir. 5 minutes, okay. Yes, sir. Mm. 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 Yes. No, it is feasible. It is feasible. No. This is what you are saying. It's okay. Here, initially, for a certain scenario, for an instant, our load is known to us. Load is known to us. Based on that known load, we supposed to calculate the current. and this current calculation is done from dead end node. And based on that we have calculate how much branch current is over there on each of this node, and next interval we calculated out whatever the voltage is over there. Voltage that means from first node, second node, and we reach up to the nth number of node. Now sir, you are saying if it is a bidirectional flow, EB is over there, or any distributed generator is over there on any nth number of node. That no, it is enough. It is enough. How? Yes, how the structure will change when we place an DG over there. At that time, what will happen? Our P demand and Q demand for that specific node will change. The moment we placed in DG or any renewable energy sources on that node, at that time we considered it as an PV bus. Yes, and it is fading the power to that particular node. Based on that, again our calculation is supposed to be carried out. Yes, this is mainly suitable. For every instant we supposed better suitable for steady state. Yes, steady state I think it's okay.
এখানেও লুজ আছে ওখানেও লুজ আছে আমি নাড়িও না চার্জারটা নিয়ে আসতে হবে আমার ফ্ল্যাশ হয়তো বা তখন সাপোর্ট দেবে না। আচ্ছা ঠিক আছে পাইলেটটা নিয়ে নিলে नहीं ये कंटिन्यू रहने दो ये कंटिन्यू रहने दो सारा का टाइम में दूसरा कर देना अभी है ना 1 घंटा बाद
Okay, let's start with second part of this. It's about the application of optimizer algorithm in power distribution system. Now, initially we'll discuss about the introduction to an optimizer algorithm. Why we need a optimizer algorithm? It's basically a task for a task of searching